Periodic properties of the elements, electron configurations, valence electrons, and the periodic table. In this tutorial, we will be going over the noble gas core electron configurations, sublevel blocks of the periodic table, the Lanthanide and Actinide series, and elements of groups 1, 2, 16, and 17. Noble gas core electron configurations. An abbreviated electron configuration can be written for elements beyond neon. The electron configuration of the nearest noble gas element of lower atomic number is represented by its chemical symbol in brackets. Neon is the closest previous noble gas to sodium. So with neon, it has 10 electrons as a noble gas, with an electron configuration of 1s2, 2s2, 2p6. Sodium has a full electron configuration of 1s2, 2s2, 2p6, 3s1. Notice how the 1s2, 2s2, 2p6 here matches the one that is right here. So the noble gas core electron configuration for sodium is that section that we see right here, represented as the symbol for neon in brackets, with only the 3s1, sodium's one valence electron, remaining. Sublevel blocks of the periodic table. The S block is groups 1 and 2. So groups 1 and 2 right here, we can see that there is an S represented all the way through here. This is where the S sublevel will be filled. The P block is groups 13 through 18. So this gold colored section right here. So if you're filling the P sublevel, you are dealing with elements in this location. The D block is groups 3 through 12. So if you're filling the D sublevel, you are dealing with elements in this location. And finally, the F block, the Lanthanide and Actinide series, which can be found at the bottom of the periodic table. So if you're filling the F sublevel, you are dealing with elements in this location. The Lanthanide and Actinide series. The F sublevel includes elements 57 through 70 found below the main portion of the periodic table. The F block elements are composed of 7 degenerate, in other words, same amount of energy, orbitals. It takes 14 electrons total to fill the F orbitals completely. Recall, there are 2 electrons maximum per orbital. The Lanthanide and Actinides are set below the D block elements to avoid making the periodic table extremely wide. Group 1 alkali metals. Group 1 atoms have an electron configuration of, in brackets, noble gas, end bracket, S1. Thus, alkali metals tend to lose the 1s electron, resulting in a stable noble gas electron configuration as a 1+ ion. So for example, lithium is 1s2, 2s1. The 1s2 right here could be, if we wanted, represented as the He noble gas in brackets, where the 2s1 represents its one valence electron. Sodium has an electron configuration of 1s2, 2s2, 2p6, 3s1, where the noble gas core is represented by the electron configuration of neon. The 3s1 represents the valence electrons of sodium. Potassium, 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, where the noble gas core is represented by the electron configuration of argon, and the 4s1 represents the valence electrons of potassium. Rubidium, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s1, where the noble gas core is represented by the electron configuration of krypton, and the 5s1 represents the valence electrons of rubidium. So what you should recognize here is that when you write these electron configurations using the noble gas cores, the only electrons that you see outside of the noble gas cores are representing valence electrons. And this is a pattern that we're going to see in upcoming slides. Group 2 alkaline earth metals. Group 2 atoms have an electron configuration of bracket noble gas end bracket S2. Thus, alkaline earth metals tend to lose the 2s electrons, resulting in a stable noble gas electron configuration as a 2+ ion. So for example, beryllium, 1s2, 2s2. This 1s2 can be replaced by the noble gas core of helium, with only the 2 valence electrons for beryllium represented. Magnesium, 1s2, 2s2, 2p6, 3s2, where the noble gas core is represented by the electron configuration of neon. The 3s2 represents the valence electrons of magnesium. Calcium, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, where the noble gas core is represented by the electron configuration of argon. The 4s2 represents the valence electrons of calcium. Strontium, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, where the noble gas core is represented by the electron configuration of krypton. The 5s2 represents the valence electrons of strontium. So again, we see this pattern as we go down this group, that every single one of the group 2 alkaline earth metals represented here all end with 2 valence electrons in the s sublevel. Group 16, the chalcogens. Group 16 atoms have an electron configuration of noble gas in bracket S2p4 for a total of 6 valence electrons that are involved in bonding. These atoms tend to gain here 2p electrons, resulting in a stable noble gas electron configuration as a 2- ion. So for oxygen, 1s2, 2s2, 2p4. This 1s2, of course, is represented by helium, with oxygen's 6 valence electrons being represented by the 2s2, 2p4 for a total of 6 valence electrons. Sulfur, 1s2, 2s2, 2p6, 3s2, 3p4, where the noble gas core is represented by the electron configuration of neon. The 3s2, 3p4 represents the valence electrons of sulfur. Selenium, and this is where things get a little bit different. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p4. So argon is going to represent everything up and through 3p6. The remainder of the electron configuration is outside the bracket of argon, 4s2, 3d10, 4p4. Now, the only electrons that are involved in bonding are those in the 4th principal energy level, so 4s2 and 4p4. Those add up to 6. We represent the 3d10 right here because it's in between energy levels, but this 3d10 sublevel is full. Let's look at our next example, tellurium. This is a long one. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p4. Again, we have the noble gas core of krypton, which takes us up from 1s2 all the way up to here. So the 5s2, 4d10, 5p4 is represented out of that noble gas core. The only valence electrons that are involved in bonding come from the s and p sublevels. 2 plus 4 gives me 6 because this d sublevel here is filled. Group 17, the halogens. Group 17 atoms have an electron configuration of noble gas in brackets S2p5, where 2 plus 5 gives me 7 valence electrons. These atoms tend to gain 1p electron, resulting in a stable noble gas electron configuration as a 1 negative ion. So for example, fluorine, 1s2, 2s2, 2p5. We have the helium noble gas core, which is representing the 1s2, and then the 2s2, 2p5 represent the valence electrons, adding up to 7, which represents, again, fluorine's 7 valence electrons. Chlorine, 1s2, 2s2, 2p6, 3s2, 3p5, where the noble gas core is represented by the electron configuration of neon. The 3s2, 3p5 represents the valence electrons of chlorine, as 2 plus 5 gives me 7. Bromine, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p5, where argon is going to represent everything here up until 4s2. The 4s2, 3d10, 4p5 is outside of this noble gas core. We see that the D sublevel is filled, so the valence electrons involved in bonding come from 4s2 and 4p5. Our last and most lengthy electron configuration is iodine. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p5, where the noble gas core of krypton represents everything up until 5s2. Then the 5s2, 4d10, 5p5 is outside of that noble gas core. Again, the D sublevel is filled with its 10 electrons, so the only valence electrons involved in bonding would be 5s2 and 5p5, where 2 and 5 add up to 7. So what did you learn? We talked about the noble gas core electron configurations. We looked at the sublevel blocks of the periodic table, the lanthanide and actinide series, and then we looked at the elements of groups 1, 2, 16, and 17. Need more help? Feel free to contact me. Have a great day.